Welcome to the Advanced Civil Engineering Training Series. Today, the focus is on a fundamental test critical for pavement design. The California Bearing Ratio or CBR test. Every massive structure, from a jumbo jet runway to an interstate highway, relies entirely on the soil beneath it. This is the subgrade. If this layer is weak, it doesn't matter how expensive the asphalt or concrete is. The structure will fail. The CBR test is the decisive tool for pavement design. This video specifically demonstrates the soaked CBR test, which is the standard for ensuring roads survive heavy rains and water saturation. The CBR is fundamentally a comparison. Imagine a material that is considered the gold standard of stability, crushed limestone. This standard rock is assigned a value of 100%. The CBR test asks, how strong is the soil compared to this rock? If the soil result is 10%, it offers 10% of the resistance of that standard rock. A soft clay might be 2%, while a robust subbase could reach 80%. Precision requires the right tools. The standard IS code equipment includes the 150mm steel mold, the spacer disc for creating volume, the heavy compaction rammer, surcharge weights to simulate pavement load, and the 50mm penetration piston. Preparation starts 24 hours ahead. To create the final sample derived from the Proctor test results, the raw soil is oven-dried at 105 degrees Celsius to remove all existing moisture. First, the empty tray is weighed. This is crucial for calculating the exact weight of the soil added later. Dried soil lumps are broken down with a mallet, and the material is passed through a 19mm IS sieve. Fine soil is collected in the tray and weighed again. Any excess is removed to match the exact sample weight derived from the Proctor test results. The exact amount of water is measured based on the Proctor test result. It is added slowly to reach the optimum moisture content. Mixing thoroughly to ensure the moisture is uniform throughout the sample. This precision is vital. If too little water is added, the soil ends up on the dry side, stiff but cracking easily. Adding too much pushes it to the wet side, causing strength to drop. Achieving that exact OMC ensures the sample reaches maximum dry density. To ensure consistent density, the soil is visually divided into 5 equal parts, one for each layer of the mold. First, let's see how a mold is created using a dynamic compaction method as per the IS 2720 guidelines. The mold is assembled with the spacer disc at the bottom, and a filter paper is placed on top to prevent sticking. The first layer is poured. Crucially, the mold is placed directly on the solid concrete floor. This prevents reverse bounce during hammering, ensuring realistic load balancing. Exactly 56 blows are applied with the heavy rammer. Blows are distributed evenly over the surface. This process repeats for all 5 layers, filling and hammering 56 times each. This builds the sample to the required density. After the final layer, the collar is removed and the excess soil is trimmed to make the surface perfectly flat. The mold is unlocked and flipped over. Before reattaching the base plate, a filter paper is placed at the bottom. The spacer disc is removed, creating a recess. Then, the 5 kg surcharge weights are placed on the soil to mimic the pavement load. This completes the mold preparation as per the IS 2720 dynamic compaction workflow. Now, a mold is created using the static compaction method as per the IRC 37 recommended guidelines for pavement design. The process here is different. The prepared soil, divided into 5 layers in the tray, is filled into the mold. Light damping is done to settle the soil, filling it to the top. The spacer disc is placed on the top. The mold is put on the machine, where a metal plate is placed between the spacer disc and the machine. A compression machine applies a slow, static load. The soil is compressed until the spacer disc is completely in line with the edge of the mold. The mold is removed and the spacer disc is taken off. The collar is then attached. Place a filter paper and the 5 kg surcharge weights on the soil to mimic the pavement load. Now, our mold is ready as per IRC 37 guidelines. At this stage, a distinction is made between unsoaked and soaked CBR. While unsoaked tests are for dry areas, most designs require the soaked CBR method. This simulates the worst-case scenario, where the subgrade is fully saturated by groundwater or rain. The procedure continues with the soak test using the IRC 37 mold. Submerge the mold in water for 96 hours. Attach a dial gauge to measure any swelling, taking readings at the start and the end. After 4 days, remove the mold and keep it fitted for 15 minutes to let the free water drain out. The mold is placed on the testing machine. With the surcharge weights in place. The plunger is seated on the soil surface. 2 analog dials are attached. One to measure the penetration depth and the proving ring dial to measure the load applied. Before starting the machine, carefully adjust both the penetration and proving ring dials to 0 to ensure accurate readings. The machine is started at a rate of 1.25 mm per minute. The engineer watches closely. For every specific interval of penetration, 0.5, 1.0, 2.0 up to 12.5 millimeters, the reading on the proving ring dial is frozen and recorded. Typically, 1 full rotation of the penetration dial equals 1 millimeter. The load is recorded at 1 rotation, 2 rotations, 2.5 rotations, and so on. Proving ring readings are converted into load values and plotted on a graph against penetration depth. The load at 2.5 mm is compared against the standard 1,370 kilograms and the load at 5 mm against the standard 2,055 kilograms. The resulting higher CBR value, in this case 12%, is taken as the final CBR. The golden rule pavement thickness is inversely proportional to the CBR value. A higher CBR means a stronger subgrade, allowing us to design a thinner, more cost-effective road crust. Engineers combine this CBR value with traffic data to design both flexible and rigid pavements, strictly following IRC 37 and MORTH standards. Incorrect CBR values or weak subgrade cause severe failures, rutting in wheel paths, fatigue cracking from stress, and potholes due to water infiltration. Accurate CBR determination ensures quality assurance and long-term performance. Getting the foundation right builds roads that last. Thank you for watching.